Proximity effect. In side-by-side located conductors carrying alternating current, the distribution of the electric current density is not uniform. The current crowding is termed the proximity effect. This crowding depends on AC current frequency. The nature behind the electric current crowding is the eddy currents induced by the nearby conductors. In this example, we will simulate two copper rods carrying alternating currents in opposite directions. The current value is 300 amperes. Conductor diameter is 30 millimeters. Distance between the conductor's centers is 128 millimeters. Frequency is 50 Hz. Our task is to determine the electric current density distribution in a conductor cross-section. Okay, let's start QuickField now. In QuickField I create new problem. Bars. Next. Model class is plane parallel. Problem type is AC magnetics. Frequency is 50 Hz. Length units are millimeters. The model axle length is 1 meter. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I will create it here from the scratch. Insert shape, circle. Conductor diameter is 30 millimeters and it is located 64 millimeters to the left from the origin. Insert. Next I will insert another conductor, and we need to add the air block. QuickField cannot simulate magnetic field distribution in the infinitely large space, so we need to restrict the simulation domain. I will insert a large circle with a diameter 1000 millimeters. Insert. Close. Zoom to fit. Here you can recognize conductors and the air. And I'm going to assign labels. Through labels I will provide material properties. Switch to Select Objects mode. Click the object to select. This is the air, and I will type in the label name here, air. Okay, this is conductor minus, and this is conductor plus. That's all for block labels, but we should also assign labels to the external boundary. This edge will have label external, and this edge will have label external. Now let's provide physical properties for the labels. Double-click the label name in the tree. For the air, I specify a relative magnetic permeability of 1. Okay. For the conductor minus, I specify a relative magnetic permeability of copper, which is 1. Electrical conductivity of copper, which is 57 megasiemens per meter, and the total current value is 300 amperes. This is the peak value of the total current. Okay. Conductor plus is again made of copper with the total current of 300 amperes plus. Okay. Far away from the conductors, the magnetic field fades to 0. So for the external boundary I assign 0 magnetic potential. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button. Now save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density. And as you can see, the current density distribution in the conductors is not uniform. That is caused by the eddy currents. You may also note that the picture looks rough. There are sharp corners on the field lines. I'm going to refine the initial finite element mesh to get more accurate results. Solve and refine. OK. Now let's take a look at the results again. Zoom in. That's better. Now I'm going to use the contour tool, draw the line here along the horizontal axis, and take a look at the current density distribution on the XY plot. The exact numbers you can see in the table. Coordinates, current density, and other field parameters. You can also use contours to calculate integrals. Contour clear. Now I'm going to select this conductor. Just click inside, follow to the integrals, total current 300 amperes as I have specified, and I can calculate the joule heat. Using the total current peak value and the joule heat peak value, I can calculate the effective resistance. Current 300 amperes, joule heat power 2.27 watts, and the resistance is power divided by the current squared. 25 microohms per 1 meter of the conductor length. This resistance value depends on the frequency. If I change the frequency to 1 MHz, which is virtually direct current, and run the analysis again, you will see that the current density distribution now is uniform, and if I use the contour tool to calculate the current, which is the same 300 amperes, and the joule heat, I can find out the resistance at the DC current. 24.7 microohms per 1 meter of the conductor length. There is another way to calculate the resistance in the QuickField. You can use the impedance wizard that divides the voltage drop by the current value, and here you can find the resistance of the conductor and the inductance as well. The difference in resistance value calculated by the impedance wizard and from the joule heat power is less than 1%. Okay, let's check now how the distance between the conductors affects the proximity effect. Open the geometry model, switch to select objects mode, select left conductor, edit, move selection to the right by 40 millimeters. OK, select right conductor, edit, move selection to the left by 40 millimeters. Now the distance between the conductor centers is only 48 millimeters. Build the Finite, open the problem properties, change the frequency back to 50 Hz. OK, save all problem files and run the analysis again. Zoom in, use the contour tool, click to select the conductor, integrals, total current is 300 amperes, and the joule heat peak value now is 2.35 watts per 1 meter of the conductor length. Let's calculate the resistance. Distance now is minus 40 and minus 40. 48 millimeters, frequency 50 Hz, current 300 amperes, power 2.35, and the resistance 26.1 microohms per 1 meter of the conductor length. If you search for the proximity effect On our website you will find the example page. Here you can read about problem setup. In fact, two cases are studied here: copper rods and steel tubes. You can read the solution section, take a look at the resulting pictures, and you can download the simulation files here. The simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free